Uh, Chapter 3, bonding, and we're going to cover bonding general concepts. Specifically, we're going to look at ionic bonding, covalent bonding, a couple of other bondings like metallic bonding, as well as VSEPR and valence bond theory and molecular orbital theory. So looking at our chapter breakdown, we're going to talk about the different types of chemical bonds. We'll talk about electronegativity, which determines whether or not something is ionic or a covalent bond. We'll talk about ions, electron configurations and sizes. We'll talk about energy effects in binary ionic compounds. 3.5, partial ionic character of covalent bonds. And then we'll do 3.6, the covalent bond, a model. Many molecules are going to be covalently bonded to each other. We'll talk about covalent bond energies and chemical reactions. We'll look at the localized electron bonding model. So how are these molecules being made? How are we taking our atoms and hooking them up together to make molecules? Then we'll go on to look at Lewis structures, some exceptions to our octet rule, the idea of resonance, and naming simple compounds. So what do we mean by a chemical bond? Well, a chemical bond is something that's going to hold two atoms together. And there's a couple of flavors of chemical bonds that we've got. Why do atoms bond with each other to form compounds? And this is all about the electrons, right? It has to do with their electronic structure and whether they're going to form an ionic bond and unevenly share electrons, or whether they're going to form a covalent bond and more evenly share them. Metallic bonds are going to have kind of a delocalized bonding paradigm where the electrons are free to move about almost like a liquid. And how do atoms bond with each other to form compounds? And that's really the most important thing that we're going to get to, is forming compounds. So a representation of molecular structures, a force that holds atoms together is called a chemical bond. It can be between atoms of the same type or atoms of different types. A covalent bond is formed when atoms share electrons. It doesn't have to be perfect sharing, but they're going to pretty much try to evenly share these electrons between each other. A collection of atoms is going to make a molecule, and molecules can be represented using a chemical formula, so CO2, which tells us the number and type of each kind of atom, or a structural formula, like here H2O, which is showing how these atoms are actually connected to each other. We also have something called an empirical formula, which gives the relative number of atoms of each element in a compound. And that's the simplest whole number ratio representation of the type and number of elements present in a molecule. Right? Our molecular formula gives the actual number of atoms of each element in a molecule of a compound. So for C4H8, the greatest common factor is 4. So our empirical formula would be CH2. There are lots of things that are going to have an empirical formula of CH2. CH2, C2H4, C4H8. Right? So our molecular formula gives us a little bit more information than our empirical formula. Oftentimes our empirical formula is easier to find out than our molecular formula. For B2, H6, the greatest common factor is 2, so its empirical formula is BH3. For carbon tetrachloride, CCl4, the only common factor is 1, so the empirical formula and the molecular formula are the same. Our structural formula gives us even more information. It's a sketch or a diagram. Sometimes you'll see it as called a skeletal formula of how the atoms in the molecule are bonded to each other. It's going to use lines to represent covalent bonds and shows how atoms in a molecule are connected or bonded to each other. For example, the structural formula of peroxide, H2O2, is shown below. So there's a bond that's being formed between this oxygen and this hydrogen, and between this oxygen and this oxygen, between this oxygen and this hydrogen as well. Okay? So to summarize, the type of formula used depends on how much is known about the compound and how much information you need to communicate. So the structural formula communicates the most information. It's got the type and the actual number, as well as the arrangement of the atoms. It's a visual picture of the compound. And we'll get to what that looks like in 3 dimensions. Right now, we're just talking about a 2-dimensional representation. The molecular formula conveys the actual type and number of elemental atoms in the compound. It doesn't tell you how each of these atoms are bonded to each other. All right, so for example, over here, maybe we've got a structure that goes H, H, O, O. right? Or maybe it's in a circle, right? We don't know from just the formula alone, the molecular formula alone. Our empirical formula tells you the least amount of information. It conveys the simple whole number relative relationship of atom to atom in the molecule. And sometimes that's enough for what you need to know, or it's what you can get a hold of in the lab. The word empirical means we have done an experiment to get this. So our empirical formula, as the name suggests, is going to be very experimentally related. We have different ways we can represent atoms and molecules. One is the space-filling molecule, which indicates the relative sizes of the atoms as well as their relative orientation in the molecule. Next, we've got the ball and stick method. Right, this is going to be a three-dimensional model, and it's going to use spheres and rods to show the connectivity as well as the atom type, right? So this white sphere is representing hydrogen, and this black sphere is representing carbon, and we can see the three-dimensional geometry, although we do not get the same idea about how much space that actually takes up. Right? Here is a summary of different ways of representing a compound. So, for example, benzene is empirical formula. Its empirical formula is CH, 1 carbon to 1 hydrogen, but its molecular formula is C6H6. So I've got 6 carbons and 6 hydrogens. Our structural formula shows the shape in 2 dimensions of what this molecule would look like. So it's carbons that are in a ring with hydrogen sticking on the outside. Our ball and stick model is going to give us a little bit more information, right? A little bit more about the three-dimensional structure. It's planar, so it's not very interesting in this picture. And then our space-filling model tells us, well, what does this look like if I actually flesh out where the electrons are going to be? Right? Now, something like ammonia down here, NH3, its empirical formula and molecular formula are the same. If we look at its structural formula in 2 dimensions, we've got nitrogens hooked up to each of these hydrogens. But if we look at our ball and stick model, we can see the 3D structure. We can begin to see that this is not just laying flat in a plane like a piece of paper. And our space-filling model gives us the most information of all. In terms of complexity, you've got more information on the right, less information on the left, more complexity, harder to draw, easier to draw and represent. Okay. Our attributes of our molecules, we've got molecules, when we talk about them, we've got some physical properties. So for example, melting point or hardness or electrical or thermal conductivity. We've got solubility. That's a chemical property. So if I take a compound and I put it in water, is it going to dissolve or not? Or is it going to form a precipitate? We can talk about electrical charge. And we can talk about bond energy. That's the amount of energy needed to form or break a bond. So these bonds, right, they're all going to be formed from electrons, right? So we're starting to bleed into a little bit of Chem 130 stuff. We're talking about energy a little bit, but it's still energy that's involved in electrons, right? So we're still dealing with everything as an electron. Right, so we've got different types of chemical bonding. Ionic bonding occurs between an atom that easily loses its electrons and an atom that has a high affinity for electrons. So something like sodium wants to lose an electron so it can look like a noble gas. It's got that S1 configuration and wants to give up an electron. Something like fluorine or chlorine wants to gain an electron. It's got that it's got that S2 P5 configuration and wants to pick up an extra electron to form a P6 and have a complete octet. Ionic compounds are typically, but not always, formed when metals react with nonmetals. So if you see this on a test, please, for the love of goodness, do not write that an ionic compound occurs between a metal and a nonmetal. All right, we will come up with a definition for what makes something ionic in a little bit, but do not say it is just between a metal and a nonmetal. An ion, as we learned before, is a charged particle. We got 2 types, either a cation, which is positive, meow, positively charged particle. It is something that has lost an electron. Metals tend to form cations, but not always. Anions are negatively charged particles. You know, this has an N and negatively has a negative N in it as well. Nonmetals tend to form anions, but not always. The beauty of chemistry is that there's a stack of rules and then an even bigger stack of exceptions. So here is your way to remember ionic bond. So this is our way to remember ionic bond. Once you know one is ionic bond, the others are probably going to be covalent. Delete up to here. So this is our method for remembering ionic bonds. Once you know what is an ionic bond, other bonds are more likely to be covalent bonds. So our mnemonic for remembering an ionic bond is bond, ionic bond, taken, not shared. So you're going to share in a covalent bond, an ionic bond is going to take. So when we are looking at bonds, the first thing we need to consider is Coulomb's law. And Coulomb's law is just used to calculate the energy of interaction between ions or any sort of charged particle. And we've got an energy term, and it's going to be related to some constant, and it's going to be related to the magnitude of the charges. So how big is your charge? Is it +1 and a -1, right? Then they're going to be attracting to each other. If it is a +1 and a -2, it's going to attract to each other more. And it's going to be divided by the radius. The further apart they are, the less attraction that they've got. So it's like absence makes the heart grow fonder. The further away they are, right, out of sight, out of mind, if they are going to be less attracted to each other the further away they are. It's like holding a magnet kind of up to a fridge and you're like closer and closer and closer and closer and whomp, and then it goes together. That's what it's like for our charges. The closer they are together, the stronger the force of attraction. E is going to have our unit of energy in joules. R is the distance between our ions in nanometers, and Q1 and Q2 are going to be the numerical ionic charges. So for the formation of sodium chloride, one electron is transferred from the sodium atom to a chlorine atom. Now, it's not a complete transfer. We'll talk about that in a little bit. For right now, we're just going to pretend it's a complete transfer. The sodium gives one up and becomes a sodium +1, where it's got 11 protons and 10 electrons, and our chlorine gains an entire electron to have 17 protons and 18 electrons. So we get a crystal of sodium chloride that forms because our sodium ions and our chlorine ions are going to be electrostatically or coulombically attracted to each other. The plus charge sees a minus charge, and they want to get together. And when they do that, they're going to form an organized structure called a crystalline lattice. And if we had a little bit more time, we would go into the nature of these crystalline structures. You get different crystal structures based on the arrangements of these atoms. There's whole bunches of different kinds. It would take a good hour and a half just to go through the basics. But because they are arranged in this kind of packing pattern where each chlorine is surrounded by 6 nearest neighbor sodium ions, and the sodium ion is surrounded by 6 nearest neighbor chlorine ions, they're going to form this nice cubic structure. Right? So if we look at the electrons and what they're doing, right, we've got our atoms of sodium. Right, here's our sodium atoms, so 1s2, 2s2, 2p6, 3s1 configuration, and it's going to lose this outermost electron to form sodium +1, which has a configuration of 1s2, 2s2, 2p6, and our chlorine, which has an electron configuration of 1s2, 2s2, 2p6, 3s1, 3p5, will gain an electron to form a configuration of 1s2, 2s2, 2p6, 3s2, well, those should be 2s, 3s2, 3p6. So if we look at our electronic configuration for our atoms, sodium starts off as 1s2, 2s2, 2p6, 3s1. It loses an electron and becomes sodium +1 with an electronic configuration of a cation, 1s2, 2s2, 2p6. This is the noble gas configuration. For neon, chlorine, on the other hand, starts off as 1s2, 2s2, 2p6, 3s2, 3p5. It gains an electron to become chlorine minus with an electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Looking at these outermost electrons, you see that we now have 8, 2, and 6 in our outermost electrons. It has gained an electron and now has a noble gas configuration. Sodium has lost an electron and it has a noble gas configuration. We call this the rule of octets because you've got 8 electrons when we're dealing with this. There are lots of exceptions to this octet rule, especially when we start getting into those transition metals, those D-boys. They are a little bit funky, but for our main groups, our S and our Ps, this is going to work out really well for us. But I just want you guys to know that it's not always going to be a nice, neat model like this. But for like our S block and our P blocks, right, rules are going to be pretty well behaved. Some common main group ions and their noble gas electron configurations. Right? If I take hydrogen, I can gain an electron, I can lose an electron and be just a bare proton, or I can gain an electron and I can look like helium. Now, hydrogen tends to want to be positive most of the time. You will sometimes see hydrides, like metal hydrides, are a pretty active area of research. Some of them are pretty rough and durable compounds. Lithium will lithium and beryllium will lose electrons. Lithium will lose one, beryllium will lose two, and they will start to look like helium. If we go down a little bit, like down to rubidium, which is a alkali metal, will lose one. Strontium, an alkali earth, will lose two. Indium, which is in that same column that we will find nitrogen in, will gain lose three electrons. Selenium, in the column that oxygen is, group 6A, will lose two. Bromine will lose one, and they will all be isoelectronic and have the same electron configuration as krypton. So all of these elements are kind of gaining or losing electrons to either complete an octet, in the case of our anions, or lose an electron to just expose and leave behind a complete octet or a noble gas configuration. And so those are going to form ionic bonds. In molecules with a covalent bond, we're still going to exchange electrons, but it's going to be more even, right? So we've got in a molecule that is going to be a homodiatomic molecule, like let's say H2 or O2 or N2, you've got a couple of interactions that are happening. You've got the nuclei repelling each other. Then you've got repulsive forces between the electrons, but then you've got attractive forces between the electron of one atom and the nucleus of another, and between the electron cloud of the other atom and its nucleus. And so they're going to share these electrons, right? So if you think about our ionic bonds as like taking something, right? Taking an electron or giving up an electron. This is more like you and your roommate. So in the first case, like you're fluorine, right? So fluorine will pick an element on the periodic table, take it down a dark alley, beat it up, take its electron, and run away laughing, and it's going to look like a noble gas, right? It has taken whatever money it's got in that atom's wallet, and now it's got that money or extra electron. Something that is a covalent bond is like, hey, dude, like if we pool our money as roomies here, like we can like both go in together and get a giant ass TV and a high-speed internet connection or a sweet car. And so you're more willing to like share and cooperate with our covalent bond. So you want to think of a covalent bond as a little cooperative or sharing. Right? So we got some nuclear attraction and repulsion that's happening, right? Attraction between nuclei and electrons, and then repulsion between both nuclei and electrons. So we kind of got this like little complex four-way diagram going on, and it is a sharing of electrons that's going to hold these things together. And so if we could get two identical atoms, right? If we got a hydrogen atom over here and a hydrogen atom over here, and we bring them together, right? Each hydrogen's got one electron. To complete its octet, it's going to have, or its octet, its noble gas configuration to look like helium, it's going to want to have two s electrons. And so what it's going to do is kind of sharing some of that electron density. As these guys get closer and closer together, our electron densities are going to start to merge together. And we'll talk about what's happening with those wave functions towards the end of the chapter, but you can think of these electrons as being shared. So now this hydrogen on the left looks like, it's like, hey man, I got two electrons. And this one over here is like, hey, I've got two electrons. Like I got the one I brought and I'm kind of sharing one with my friend. So they are together sharing some of those. If you do a plot of internuclear distance, like how far apart are they? If they're too far apart, our interactions are weak and no bonding occurs. That's like up here, right? Nothing's happening. If we bring them too close together, right now they're like all up in each other's grill, and it's like my proton and my protons in my nuclei are getting way too close to each other. The energy goes way up, right? It doesn't want to be there. And so it's going to move those guys apart, It doesn't want to go too far. It's going to reach this energy minimum and where they're optimally separated. So our energetic minimum, right? We talk about electrons and molecules being lazy. They want to be at that energy minimum. And for us, that's going to be 74 picometers in between one hydrogen nucleus and the other hydrogen nucleus. And that is the bond length. So another way to view this, right, is we've got one nucleus, another nucleus, and they are kind of sharing and overlapping their two electrons. And we're going to represent this in two dimensions, or simplistically with our skeletal structure, as being a bond. So if you are sharing two electrons, right, what can you draw between 2 points? You can draw a line. And so we're going to draw a line between these 2 points. And so this hydrogen's got a line on it. It thinks it's got 2 electrons. So this hydrogen's got a line on it. It thinks it has 2 electrons on it. A line between 2 atoms represents a shared electron pair or a covalent bond. Each atom of hydrogen sees 2 electrons, or it thinks it's got the noble gas configuration for helium. Our bond length is defined as the distance between 2 atoms where the energy is lowest. So if you look back on that previous figure, the energy in terms are net potential energy and kinetic energy. 0 point of energy is defined when the atoms are in infinite separation. So like if you take that nucleus and you move it all the way apart from the other hydrogen nucleus, right, we've got no energy. If they're infinitely far apart, there's no attraction to each other. Because if you look at Coulomb's law, remember that guy was related to the inverse of the distance between them, right? The further away you moved them, the less attraction they've got. You move them infinitely far apart, no attraction. Energy tends to rise steeply when you get them too close because of repulsive forces of those nuclei and when the atoms are in close proximity. So if we look at our H2 molecule, our electrons are going to reside in the space between the 2 nuclei. So we've got simultaneous attraction leads to increased stability compared to single H2 atoms or hydrogen atoms. Increased attractive forces cause a decrease in the potential energy of the electrons. So we want to minimize that energy. Our atoms don't want to do work. Our molecules don't want to do work. We want to minimize that energy as much as we can. If we take a molecule and we put it into an electric field, right? And I've got a hydrogen and a fluorine molecule. Here I've got a covalent bond that has happened, but I've got a pretty uneven sharing. It's almost an ionic bond. So if I've got this thing that's called a polar bond, and I apply an electric field, well, one of these, fluorine, right, is pretty electron greedy. It's going to move most of this electron, right? It's like sharing stuff with your big brother, right? Your big brother comes and it's like, yeah, I'm going to share this, and it's got it and he's got it most of the time. And then you're like, do I ever get to play with my stuff? And it's like, yeah, maybe a little bit, just so the mom doesn't get mad, right? So my fluorine is going to be a little bit more negative because it's got a little bit more electron density than my hydrogen. If I put that in the presence of an electric field, right, I put a potential on these plates, apply a voltage, these guys are going to snap to and align up in that electrical field, where the positive end with my hydrogen will be attracted to this electrical plate, and the negative end is going to be attracted to this positive plate. And that's how LCD displays work. That's how instead of having like a hydrogen molecule, they've got a very long chain molecule that will go from an ordered state to a disordered state that's going to affect how polarized light travels through these molecules in our liquid crystal. So they'll either be disordered and you apply a voltage and they'll become ordered, or vice versa, and that's either going to block or allow polarized light to come through. So if you take a pair of polarized sunglasses, for example, and then look at your computer monitor and turn your head left and right, or your cell phone, you're going to see that kind of fade in and out because the light that is coming from that screen, right, from an LCD screen, liquid crystal display screen, is going to be polarized. It's real obvious if you got a simple one like on a calculator or at a gas pump that's just a simple alphanumeric display. All right, so that's one of the ways we're going to actually see these polarized bonds and polarized molecules show up. Our polar covalent bond is an unequal sharing of the electrons between atoms in a molecule. They're going to result in charge separation on the bond and a partial positive and partial negative charge on the 2 atoms that are involved in that bond. Now, can a particular atom be bonded to more than one other atom? Yes. So if you look at something like methane, CH4 carbon. That carbon is bonded to 4 methanes, but you're not going to have that one bond really shared between 3 different atoms. But we will talk about something called resonance, where you can kind of do that a little bit. But basically, you want to form 1 or 2 connections between an atom, 1 or 2 bonds, or 3 bonds, or 4 bonds between one atom and another atom. And you kind of want to treat these bonds as being separate, distinct things, right? So what do we mean by chemical bond? Right? That's going to be sharing of electrons, whether it is a very uneven sharing in our ionic bond to where it's practically taken, whether it is unevenly shared, like in our covalent but polar bond, or whether it is going to be very evenly shared in what we call a non-polar bond. Why do atoms bond to form other molecules? Because we want to reach that lowest energy state, right? That's often achieved by forming a complete octet, so that those electrons are going to be in that stable octet noble gas configuration. How do atoms bond to form other molecules? Well, it can either be covalent or it can be ionic. One of our determining factors in this, right, do I have a covalent bond? Do I have an ionic bond? Do I have a polar covalent bond? Is something called